So today we're going to look at the Servotube emulator so that someone can connect to like an Allen Bradley incremental encoder with Hall motor. This motor has a sine cosine reading the magnets, so it's analog Hall, analog feedback, 1 volt peak to peak, sine cosine differential. The rod is the magnets, the little sensors, analog Hall sensors. Sine and cosine come off here and go to the drive. But the Allen Bradley can't take in, they need the Halls, an incremental encoder. So there used to be a little adapter, interpolator, they call it the interpolator, and you put the motor in here, the feedback goes in, and then output goes to the controller, just a normal, whatever you want to use to control it, but sine cosine comes in, +5 and ground, take the temperature and feed that right into the drive. You don't need to go through this thing, it's just a pass through. But you get some Halls, UVW, and you get some encoder AA0, BB0. I don't see an index, that's fine. That doesn't make sense anyways, because there is no index. Maybe the zero crossing of the sine wave. So as you go through the electrical cycle, you get Halls. There's a chart here. I'm not saying this chart is right or wrong. I'll show you how we're going to use the Copley drive to be an emulator. The one thing I noticed here, it says 10 microns. And I don't get it, right? So you can't do that with 12-bit AtoDs unless you're like fudging it a little bit. But hey, it's 10 microns with some noise. It's not 10 microns of accuracy, that's for sure, because they're magnets and you're measuring the magnets, and magnets are stacked, and so it's definitely not accuracy. But let's do like 4096 divided by 71.2 millimeters for the pitch. I get about 17 microns. So, well, maybe 20 microns. You could round down, just take the 7 off, and then you're back to 10 microns again. Just to double check this, yeah, here's the pole pitch, 1 electrical cycle for the 34 millimeter motor. There's a 25 millimeter and a 17 millimeter, and those will have 10 microns. But the 38s, right, that's not 10 microns. But, accuracy, effective number of bits. Anyways, if we move from a drive that has 12 bits to one that has 16 bits. So this is our module, right? It's not a big package like the interpolator, but it's just a little module. If you don't have a board to plug that into, then you get a little easy board and you hook up your feedback, and then you take it out on the I/O connector and the emulated encoder out, and there's a serial port to connect to. But this is 16 bits. So it's got 16-bit AtoDs in it. So not only can I get the right amount of interpolation out of this thing for moving a certain distance, right? This is the 4096 plus or minus a bit, so it's 12-bit AtoD for sure, giving it a 4096, so there's no noise there. I set this up by pressing set 0, and then it, as it goes plus or minus a count, then you can see, the count here. So there's not much noise with 16-bit AtoDs, but it's enough to get an occasional trigger on a count. But we can go to 16 bits of resolution. So that's a lot more. That's like a 1 micron. Okay, so not divided by 4096, but 16384. So let's do a setup here on the setup screen, change the settings. So low frequency analog and analog, linear brushless. So this is sort of the default for the interpolators or emulators, but we can put 65536 in there. So it's going to go from 12.5 microns for this size 25 motor. It's a 51.2 millimeter motor. The resolution is allowed, but accuracy and repeatability, okay, plus or minus a few bits. So, all right, less than 1 micron, 780 nanometer. And so that's the configuration. And then we can again zero, open up the scope there and hit record. And let's zero it out. So make this the 0 position. So I got a little bit of noise. Sure, you know, around 0 I get plus or minus a few counts. And if I zoom into that, plus or minus 2, 3, 4 counts, that's sort of the quantization. There's a few outliers there, but okay, so it's you know, 1 micron worth of resolution, but plus or minus a few bits of noise. Some pretty good E-knob on a 16-bit AtoD, but you know, what would you expect? So what I'm going to do to trigger this is I'm going to go a little bit negative here, okay? And now that I'm waiting for a trigger, you'll see what I'm going to do is I'm going to make a move. This is a 25 millimeter diameter rod, so that's got the 51.2 millimeter pair of magnets. So I'm going to go from 51.2 millimeters on my scale here up to 0, and hopefully that'll trigger the scope on a rising edge going through 0. Let's hope that did that. Reading trace data. So there it is. You can see the Hall states, okay, and the sine and the cosine and the move by hand, and the count goes up to 65536 from 0. So, or I was a little bit behind there. But the point is I went approximately 51.2 millimeters and I get this sort of resolution. I should show how I got the outputs 1, 2, and 3. So again, on this drive, out 1. And if it was a fault, you can change it. First disable, but I got out 1, 2, and 3, 5-volt logic. Perfect. You know, not the 3-volt logic, but the 5-volt logic for typical Halls. And to configure this from the software, we use the ASCII command line to set 0x70, 71, 72, and 73. ASCII can get from RAM 0x70. There. And so I could, let me get it from 71. So 120 degrees, 72, 240. You could start at 30 and go in increments of 120. You could start at 0. So whatever it takes, you know, swap wires or phase in your Allen Bradley, or I guess ask for help and we'll connect the serial port and troubleshoot it. But I did 30, 150, and 240, 56, 270 for the one with the minus 180 Hall offset. And that worked good for the emulator. We sell that as the ADP AccelNet 2000 82111, the 82111. But this, I'm using the ACK APV 180, whatever the lowest cost one is, with the easy board, easy to connect to. And I get 16 bits or 1 micron worth of resolution. And that's the goal. Also, when you save those values, so set in flash 0x70. 8 space 0. So you also want to set these in flash too. So 71 gets set to 120 in flash. 72 gets set to 240 in flash. And again, you could do 30, 150, 240, 50, 270. That's fine. And see here, I think that's about it for, let's just see what's, yeah, so we made a move up to that 65536 plus or minus a few counts. So here's about 5 counts on that. And yeah, 51.2 millimeters. Yeah. Oh, the last thing was the noise. Like, I'm just measuring the rod, right, and it's picking up AC line noise, like, because it's not connected to earth. So maybe the shaft of the motor should also find a path to earth. It's not a lot of noise, but when you got a PWM amplifier, you want to be conscious of noise. Yeah, so Hall states UVW output 1, 2, 3, sine and cosine, about 1 volt peak to peak, 90 degrees out of phase. That's good. And so here's the back EMF chart, you know, for this configuration. If somebody needs to enter this chart into a drive, I'm not sure how they do that, but we have manual phasing, so we'll just put it on, spin the thing, and check the phasing. But we can shift it for you. So get the serial cable. I've got a USB to RJ11 here in my system. So, you know, USB on one end, RJ11 on the other. Just plug it in, and you're talking. And oh yeah, ignore the under voltage fault. I'm running this off at 24 volts. If I hooked it up to the HV, then the under voltage would go away. Don't enable the drive because you don't want to output. You know, maybe if you're trying to use an Allen Bradley, you should check with Copley, see if they have Ethernet IP SIP working yet. That's something that's been under development. We got Modbus, TCP/IP.